All right, well, my clock here is showing 2:15, so we can go ahead and get started. All right, it is Thursday, January 12th at 2:15 p.m. here in Seattle, Washington, and I'm very happy to welcome you to the final press conference of this 241st meeting of the American Astronomical Society. I'm going to be your host this afternoon. I am Kerry Hensley, the Deputy AAS Press Officer, and I'm assisted today by our AAS Media Fellow, Ben Cassess, and our Astrobites Media Intern, Zilly Shen. So I'd like to ask you to go ahead and silence your cell phone or anything else that might make noise out of respect for our presenters. There will be several press releases distributed associated with this afternoon's presentations, and all of the webcast videos for all of the previous press conferences have been uploaded to the press kit. They're also available on the AAS Press Office YouTube channel, and you can find lots of other fun things like presenter slides and press releases in the press kit as well. So just a brief introduction to how AAS press conferences work, if this is your first one of the meeting or your first one ever. I'm going to give a brief introduction to our topic and our panelists, and then we're going to hear from them one by one. We're not going to break for Q&A in between their presentations. We're going to do group Q&A from the people in the room as well as anyone watching on Zoom collectively afterward. So our final press conference of the meeting is on signals from black holes and neutron stars. So we're going to hear 4 perspectives on detecting and deciphering these signals. Our first presenter is Eric Coughlin from Syracuse University, speaking on Live to Die Another Day, discovering a repeating partial tidal disruption event. Next, Emily Engelthaler from the Center for Astrophysics, Harvard and Smithsonian, will speak on ultraviolet spectroscopic analysis of a tidal disruption event. Next, Rose Xu from Bard College will speak on the detection of 7 high-energy X-ray flares from the Milky Way's supermassive black hole. And our final presenter, not just of this press conference, but of the meeting, saving the best for last, is Amruta Jaodand, speaking on a pulsar. In fact, from California Institute of Technology, speaking on the discovery of an ultraviolet millisecond pulsar. So with that, I will turn things over to our first speaker, Eric.
Okay, so thanks, Kerry, for the introduction. Thanks, everyone, for being here. My name is Eric Coughlin. I'm a professor at Syracuse University in the physics department. And today, what I'm going to be discussing with you is a result that we just had published today, actually, in the Astrophysical Journal Letters. If you follow that QR code, it'll take you to a preprint version of the paper, but the published version is also freely available if you want to look into the details of what I'm going to be describing today. And so what am I going to be talking about? I'm going to be talking about this very peculiar and interesting astrophysical transient AT 2018 FYK. So AT stands for astrophysical transient. Transient is a source that rises and fades in brightness on the night sky on human timescales. In this case, we're talking about months to years. 2018 was the year in which the source was originally detected, and then FYK is just the string of letters that we use to identify this specific source, because we see many of these things per year. And what I'm going to describe is the model that we propose to explain this very peculiar transient, namely that this is an example of what's called a repeating partial tidal disruption event, or a star that is being periodically snacked upon by a supermassive black hole. Okay, so at the heart of what we think is powering the emission from this source is a supermassive black hole. So black holes are among the most interesting and enigmatic predictions of Einstein's general theory of relativity. Essentially, they're a region of space and time that is so densely populated with mass and energy that the gravitational field produced by that mass and energy is so strong that not even light can escape from the gravitational influence of this object. And so, as their name would seem to imply, black holes emit little to no light, hence they are black. We can't see them. But counterintuitively, we've actually just recently directly detected 2 supermassive black holes. So the one on the top M87 star, this is the supermassive black hole in the nucleus of the galaxy M87. This black hole has a mass 6 billion times the mass of the sun. That's why they're called supermassive. They have masses anywhere from millions to billions of times the mass of our sun. And then the one on the bottom is Sagittarius A star. This is the supermassive black hole in the nucleus of our own Milky Way galaxy with a mass of 4 million times the mass of the sun. So, but what you can see from this image is that we don't directly detect the black hole itself. The black hole is sort of the shadow in the centers of each one of these images. Instead, what we see is this kind of like luminous halo surrounding the black hole. And that's emission from the gas in the immediate vicinity of the supermassive black hole. So what we need in order for a black hole to reveal itself to us is gas in its immediate surroundings. And unfortunately, most supermassive black holes throughout the universe, something like 98%, do not have a consistent supply of mass in this form, and hence they're what we call quiescent or dark. And so directly detecting supermassive black holes is not such a simple feat. But interestingly, occasionally a star in a distant galaxy can have an unfortunate close approach with the supermassive black hole. The star can get so close that it actually starts to experience significant what's called tidal distortion. So it's substantially modified by the gravitational field of the black hole to the point that it can actually be ripped apart by the gravitational field of the supermassive black hole because the gravitational field is so extreme. And so what happens is that the star, the shredded stellar material, actually returns to the supermassive black hole and provides a brief supply of gas to the black hole that then gets extremely hot and luminous, and we can detect the emission from an event like this out to cosmological distances, so millions of light years away. And this whole process of destroying a star by a black hole, feeding it shredded stellar material, having it light up and outshine the entire galaxy in which the black hole resides is known as a tidal disruption event, or a TDE. And so these events by themselves are extremely useful probes of the nuclei of distant galaxies and supermassive black holes. And nowadays, we're detecting events like this fairly regularly, so on the order of dozens per year. So AT 2018 FYK, remember this is an astrophysical transient, originally detected in 2018, was thought to be an example of a tidal disruption event. And so what I'm showing you here on the y-axis is the luminosity. This is the energy per unit time emitted by this source. Think about it like a light bulb, except this is just an extremely energetic version of a light bulb. So the y-axis is just giving you a sense of how much energy is pumped out by this source. And this is as a function of time in days since the original detection. So this thing was turned on for 600 days or so since it was originally detected, since it was originally seen. And then the two colors are just giving you different wave bands in which we detected this source. So the green curve is giving you the emission in the optical and UV light that you can see with your eyes. And then the black curve is showing you the X-ray emission from this source. And so this is an example of an X-ray bright TDE, which are relatively rare. And so what you can see that's sort of interesting about this source, even when it was initially detected and discovered and followed for the first 600 days, this is in a paper by Thomas Wevers and DJ Pasham, who are also co-authors of the current paper that I'm talking about, is that around day 600 after it was discovered, this source abruptly plummeted in its total luminosity and fell by 3 to 4 orders of magnitude and was below the detection threshold of both in the UV and in the X-ray. And that by itself was actually kind of strange because TDEs, tidal disruption events, are not actually predicted to do this sort of thing. And so in this paper, the authors speculated that perhaps something changed with the accretion flow or the gas surrounding the black hole that caused this to happen. But what was even more surprising is that 600 days after that, after this source went into quiescence, or almost 4 years after it was originally detected, we went back and looked at this object again and found that it was once again bright in both the optical and UV to levels that were comparable to the initial values when it was, first detected. And that's really, really weird. And that's not at all predicted by standard theories of TDEs. And so when we saw this, we had to come up with some new sort of explanation to propose to explain this really weird behavior of why this TDE would suddenly come back to life 2 years after it faded. What would possibly be causing it to do that? And so to help me explain it, I have the voice of Thomas Wevers and this nice animation.
Stars in our universe can be destroyed by the gravitational field of a supermassive black hole. This astrophysical phenomenon generates a luminous outburst and is known as a tidal disruption event, or TDE. Typically, the star is completely destroyed during the tidal interaction with the black hole. But occasionally, when the star is only partially destroyed, an event known as a partial TDE, the surviving stellar core, stripped of its envelope, recedes back out into the host galaxy of the black hole. Thus, scientists have usually considered TDEs to be once-and-done events. However, contrary to this standard picture, a team of astronomers led by Dr. Thomas Wevers tracked the TDE AT 2018 FYK and found it to re-brighten nearly 4 years after its initial discovery. The team proposed that AT 2018 FYK is powered by a repeated partial tidal disruption event, where the star survives in orbit about the supermassive black hole and is stripped of mass every time it reaches its point of closest approach, roughly every 4 years. Thus, it is a periodic snack for the black hole. Prior research suggested that such an orbit would take hundreds or even thousands of years. The observed 4-year orbit of the unfortunate star therefore implies that it must have been part of a binary system with another star, as this alters the dynamics of the event, with orbital energy kicking out the high-velocity star and allowing the bound component to orbit the black hole with a much shorter period. The study of this repeated partial tidal disruption event gives unprecedented insight into the existence of supermassive black holes and the orbital dynamics of stars in the centers of galaxies, and suggests a new paradigm for the origin of periodic flares from centers of external galaxies.
Okay, so that's the story. That's the model. We think that there's actually a star that's being repeatedly stripped of mass in the center of this distant galaxy that's then fueling these accretion flares that we're detecting periodically, once every 600 days or so. And so an interesting corollary of this model is that there's actually a prediction, which is that this source should undergo another abrupt dimming event and fade below detection levels once again in August of this year. So we're actively monitoring this. We're really interested to see if this actually happens, if the model holds up. So stay tuned. And then if you, obviously, if you want to ask me any questions, I'll be here for the Q&A, but then I've also put my contact info up here if you want to reach out directly. Thanks.
How do I escape? There's too many things on the screen. That's fair. Okay, hello, my name is Emily Engelthaler, and I've been working with my advisor, Peter Maxim, to do ultraviolet spectroscopy of a specific tidal disruption event that was discovered this year. And in case you missed the abundance of explanation of what a tidal disruption event was, I've made a cartoon for you where we have a supermassive black hole in a star that gets too close and gets ripped apart and spaghettified. And yes, that is the technical term. By this black hole getting wrapped around, some of it will get launched off and some of the star will end up getting wrapped around into an accretion disk. And our black holes are very messy eaters. And so while, first of all, they're eating this accretion disk donut-shaped thing from the inside, and they're eating too much and they're spewing out radiation as they do so, making this accretion disk puff up into a nice big fat donut for them to eat, and also sometimes spewing things out in a jetted form as well. And what we will be looking at with the spectroscopy is the radiation that's coming through this disk. So these are the 3 spectra that were taken with Hubble. Ultraviolet is very bad at getting through our atmosphere, which is great for us, but terrible for observation. So we have to use a space telescope.
And we've been trying to observe how this spectra changes over the course of several months as these tidal disruption events are changing over the course of months. As you can see, there is a fairly significant overall change between the one that was taken in about 2 months and the one that was taken in about 4 or 5 months. In all cases, we noticed that the spectra were excellently fit with a black body, which is great. That's a simple model. We can get a temperature from that. We can see how the temperature is evolving over time. And we can also just subtract that model out so that we can then look at the emission and absorption lines with a lot more certainty and clarity. So one of the most prominent things we see in our spectra are blue shifted features. Here are 2 of them. One is a nitrogen 3 line, another is a carbon 4 line. If you look to the one, no, you cannot see my cursor. If you look to the absorption line to the side, the very skinny one is actually just Milky Way contamination, but the broader one is the blue shifted carbon 4. The red lines in each case are where we would expect to find the line if it was at rest. It is not at rest, it is at shorter wavelength, which means that we have material flying towards us, which is expected. But in the case of the carbon, which is actually one of our most prominent features, this means we have things traveling towards us from this tidal disruption event at thousands of kilometers per second, which is not insignificant. Now, the other thing you'll notice in the carbon 4 plot is that close to at rest, we have this double bump fit here. Now, this is actually an absorption and emission that are overlapped on top of each other. We also see this even more prominently with the Lyman alpha emission. Lyman alpha hydrogen line, it is not surprising that this is also our most prominent feature in the spectra. And in both the carbon 4 and the Lyman alpha case, as well as some other lines, the absorption is both a little bit more blue shifted and is narrower than the emission from the same element, which would suggest that we have optically thick material traveling more directly towards us with less variation in velocity, and the optically thin material traveling still towards us because it's still blue shifted, but not as directly. And then this is just our best guess as to what this extra hump is here. Now, we also have a lot of variability with these spectra. So what I was showing you earlier was all features from the first spectra, which is also the clearest because there is still the most energy. As you can see here, I have shown you again the carbon 4 features we were looking at. And overlapped on top of that are the other 2 spectra, along with smooth versions of all 3 spectra. And you can see that it has disappeared. Now, whether this is just there's not enough energy to make a clear absorption line at this point, so it's just disappeared into noise, that's one option. But another couple more interesting options, because there should be enough energy that we could see something there, would be one, we just simply don't have enough energy to reach that ionization level, or because the energy is, as it decreases over time, as the accretion decreases, this means that the radiation winds are going to decrease, and that puffy donut that the black hole is eating is going to get thinner. And if the material simply moves out of the way from our line of sight, it's not going to absorb, and we are not going to see anything. And so in summary, we were looking with spectroscopy at a star getting ripped apart by a supermassive black hole. There was a high variability with these features over the course of several months, including both features disappearing, the temperature decreasing, and there's also some possible overlapping, well, there's many overlapping features, that's part of the fun of spectroscopy, but also we have some features that appear to be from the same element, both absorption and emission overlapping each other at the same time. And while there are only a handful of tidal disruption events that have been observed with UV spectroscopy, we hope to have more in the future. And my contact information is at the bottom. Thank you.
I need your help to pull up the slides. Thank you. All right. Good afternoon, everyone. Now let me bring your attention to our cosmic backyard and take a look at our own supermassive black hole. I am Rose Xu from Bard College. My advisor is Shuo Zhang. She has joined us virtually. Today, I'm presenting to you our newest detection of 7 high-energy X-ray flares from the galactic center supermassive black hole Sagittarius A. This work is carried out with our collaborators across the globe. Most massive galaxies harbor supermassive black holes in the center. Our own Milky Way galaxy has no exception. Located at 26,000 light years away from Earth, the center of the Milky Way is the home to the closest supermassive black hole to us, called Sagittarius A star, or in short, Sag A star. It has 4 million times the mass of the sun. This video on the right takes you all the way to the center of our galaxy and shows a close-up X-ray view of Sagittarius A. Sagittarius A also happens to be one of the least active supermassive black hole to us. However, it is by no means boring. In fact, Sagittarius A has attracted a lot of attention from astronomers because of its mysterious flares. Despite inactive nowadays, Sagittarius A demonstrates flaring activity on a daily basis, which are most significantly observed in the X-ray and near-infrared energy bands. Each flare lasts up to a few hours. But when exactly a flare will start or stop is not predictable as for now. To be honest, we sometimes need a bit of luck to capture one. And during a flare, the X-ray luminosity of Sagittarius A would increase as high as 600 times of the baseline level, the so-called quiescent luminosity. For example, here is a pretty bright flare detected by Chandra. And in this case, Sagittarius A's X-ray luminosity increased to 245 times of the quiescent luminosity. So why are we interested? Why are we interested at all in these cosmic fireworks put on by Sagittarius A? Well, there are a couple of reasons. First, this type of flare are uniquely detected from 2 nearest supermassive black holes. One is Sagittarius A for sure, and the other is M31 star at the center of the Andromeda galaxy. And secondly, and most importantly to myself, these flares take place at only a few gravitational radii to Sagittarius A. So they can serve as an ideal probe for the physical conditions at the vicinity of this supermassive black hole. By studying those flares, we could infer like electron density and magnetic field strengths right next to the supermassive black hole. These fascinating flares have triggered many theoretical models to try to explain the physical origin. The most popular model suggested by the gravity observations is a magnetic phenomenon, as you can see in the simulation. It involves a plasma blob orbiting around the black hole. A competing model is a transient phenomenon, for example, an asteroid being disturbed by the black hole. So that is exactly the big question that both observers and theorists want to answer. What is the physics behind these flares? To answer that question, the New Star X-ray telescope has been monitoring Sagittarius A since its launch in 2012. By the end of 2022, we have accumulated more than 2 megaseconds of data, equivalent to 46 days of observation. Over the years, New Star has teamed up with various observatories for joint Sagittarius A observation campaigns. For example, jointly with the Event Horizon Telescope and the Gravity Telescope, aiming to reveal the mystery of Sagittarius A flares. Using the first 1 megasecond of data obtained between 2012 and 2015, our team has found a total of 7 bright hard X-ray flares. Today, I'm going to show you the newly detected flares using data obtained after 2016, as highlighted in yellow in this table. Using 1.3 megaseconds of data obtained between 2016 and 2022, we detected another 7 bright Sagittarius flares. Here, let me showcase the light curve of 3 of them detected in 2018, 2019, and 2022, respectively. Just a reminder that a light curve plot tells us how the brightness of the black hole changes over time. Flare number 1 on the top left corner was detected in August 2019. It is one of the longest flare that new star detected. This one lasted for about 2.5 hours. Although new star didn't catch the peak of this flare, you can see that the increasing and decreasing stages are clearly captured. Flare number 2 on the bottom was detected a couple of months ago in April 2022. This one lasted a full hour, and you can tell from the graph that Sagittarius luminosity took only 10 minutes to get to its peak, and then used another 30 minutes to drop back down to the quiescent luminosity. Lastly, I really want to highlight this 4-hour bright flare detected in April 2018 on the right, where you can see a clear double peak feature. Here is the zoomed in light curve of the double peak flare. After reaching the first peak, Sagittarius took only 15 minutes to recover and then reached the second higher peak. Such a dramatic change suggests that the physical condition, for example, the magnetic field strength, has to recover very swiftly in order to enable that second higher peak within a very short amount of time. We are now still deeply puzzled by what kind of mechanism enables this recovery. As you can see, Sagittarius flares have different duration, brightness, and variability. An important question we have been investigating is whether brighter flares and fainter flares share the same physical origin. And to answer that, we studied flare spectrum dependence on their brightness, or the flux level. In this plot on the left, I am showing you flare spectrum shape dependence on their flux level. A reminder that smaller photon index is equivalent to a harder spectrum, meaning more photons falling into the higher energy bands. The black data points represents the 7 previously detected flares between 2012 and 2015. And the red data points represents the 7 newly detected flares in this work after 2016. By feeding OD14 flare data points, we found a weak trend showing that brighter flares tend to have a harder spectrum. This trend is detected at a 2 sigma confidence level right now. While we cannot fully confirm this trend, our results suggest that brighter flares and fainter flares might come from different physical origins. We definitely need more data to confirm or reject this trend. Just to sum up, we detected 7 bright hard X-ray flares from Sagittarius, which doubled the known number of bright hard X-ray Sagittarius flares as reported in the literature. We found a trend indicating that brighter flares have harder spectrum comparing to the fainter flares, but we need more data to confirm this. Thanks for your time. My advisor, Shuozhang, and I welcome your questions afterwards.
Okay, good afternoon. Thank you for being with me through this press conference, especially as this is going to be the last of the talks. My name is Amruta Jaodand, and I am a postdoctoral researcher at Caltech. Today, I'm here on behalf of my collaboration to talk about the discovery of UV millisecond pulsations in a pulsar 1023 plus 0038. So we're going to switch tracks a little bit from black holes now. What we have discovered is that we see UV millisecond pulsations with Hubble Space Telescope. The pulse period is about 1.69 milliseconds, making it currently the fastest known ultraviolet pulsar. It has been found in an old system which comprises of a millisecond pulsars. I'm going to take you through what these systems are in a second. So when a massive supergiant star gets old and exhausts its fuel, it dies in a fiery explosion called supernova. During this explosion, as the external shell dissipates, we are left with a really dense core called as the neutron star. It's supported by the degeneracy pressure. Now, these neutron stars are really fascinating objects because they are about 6.2 miles in their radius and comprise as much mass as 1 to 2 times the mass of our sun. Additionally, not just being dense, but they also have intense magnetic fields, so about 100 trillion fridge magnets worth. And gravity, which is about 2,000 million times what we experience on our planet Earth. And to compound and add more to this mystery is that these stars rotate faster than your ordinary kitchen blenders, or some of them rotate about 500 to 600 times in a second. And this is what I've been researching as how do they get to these speeds? So some of the neutron stars that, because they're rotating this fast and they have intensely high magnetic fields, they are able to accelerate particles that are around them along the magnetic field lines and produce intensely energetic emission that comes out of their pulse. As these beams sweep our line of sight or our detectors, such as the radio telescope, for example, a Green Bank telescope or Arecibo, which used to be my favorite radio telescope, we register these pulses. In fact, registration of these pulses is how initially, if you can see, there's a small little scruff that you can see in this chart recorder data, is how Jocelyn Bell Burnell found the first radio pulsar in 1967. Since then, we have found lots of pulsars, and we know about 3,359 pulsars that are currently known. And based on their properties, such as how intense is the magnetic field, how rapidly they are rotating, how old they are, we can broadly classify them in different groups. So we have the most energetic young pulsars. As they get older, because they are spinning and emitting such an energetic emission that comes out through their spin down luminosity, they enter a region called the normal pulsars. As they get older and the emission weakens, they enter this bottom right part of the diagram called as the pulsar graveyard. This is officially the time when we stop seeing them in our detectors. Now, what happens is that sometimes some of these pulsars can have companions that can transfer angular momentum and mass onto the pulsar and spin it up or torque it up to extremely high spins, emerging as a millisecond pulsar. This phenomena is called pulsar recycling mechanism. And currently, we know of about 360 millisecond pulsars detected in radio, gamma rays, and X-rays. Now I would like to introduce you to a system that I've been studying for the past few years, which is very fascinating. So in the constellation of Sexton lies a system which comprises of a pulsar in a tight binary orbit with a companion. This pulsar rotates about 600 times a second, and we see it in form of the green color energetic radio emission that's coming out of it. Now, sometimes over a course of just a few days to weeks, this system stops emitting those radio pulsations. And instead, we see the pink glow, which is positionally coincident and indicates that the companion has managed to overshoot the hold of its own gravitational potential and has started accreting matter onto the neutron star via formation of an accretion disk, or like a thin geometric disk that sits around the pulsar. So we are going to call the first state where we see radio pulsation configuration A, and this would be the configuration B where the accretion disk is formed. So these systems that I've been studying are called transitional millisecond pulsars because they switch between these two configurations really rapidly. And as they switch from one configuration to another, specifically the pulsar 1023 plus 0038 that I'm talking about today, we see also that their pulsations, the pulses that we were receiving, change form. So they change from radio pulsations to X-ray, UV, and optical on really intense time scale. This poses a problem for our pulsar emission models. And initially we had thought, okay, theoretically, X-rays originate closer to the pulsar, and then UV and optical emission should be closer to the companion object. And so we obtained a multi-wavelength campaign, which comprised of Hubble data in UV and X-ray data from NuSTAR, XMM Newton, and optical data from Kepler. So if you look at the Hubble spectrum for this system, you can see that we are able to model out the companion's contribution, and this way focus just on the wave bands that correspond to the pulsar. Because we previously knew that there was a radio pulsar in the system before it had transitioned from configuration A to B, I was able to use that information to construct a search pipeline that would look for pulsations in the Hubble data. And what it led to is the detection of the first UV millisecond pulsar. So in this diagram, you can see the two profiles, which basically capture which part of those energetic pulsar beams that are passing by us we are sampling when we stack them up. And so on the bottom panel is the X-ray pulsar profile, this pulsar signal, and on the top curve is for the UV Hubble data. Previously, the UV pulsars that we had known were just younger systems. For example, one of the most famous example is the UV pulsar Crab. And all of them were younger than 10,000 years or so. These systems were discovered as early as 1969. And so it has taken us 50 years now to be able to detect the first millisecond pulsar in UV. The other thing is now, does this discovery point to an unexplored population? Because if you're looking at this diagram of luminosity versus how old a pulsar is, the pulsar 1023 plus 0038 in UV stands out as an entirely of an outlier system that lies in part of the luminosity age diagram, which was or has not been probed before. Does that mean we are going to be able to find new systems? And that's my hope, as I have been working with the proposed UVEX mission at Caltech, and we hope that more of such systems would be found. So to summarize, we have discovered the first ultraviolet millisecond pulsar with Hubble telescope. It is rotating pretty rapidly at a spin period of 1.69 milliseconds. Since our discovery, similar phenomena has also been found in another accreting systems, although at levels that are way more energetic than us, called the SAX 1808. And it's great because that confirms our discovery and tells us that this discovery of UV millisecond pulsations is not a fluke. Now, the questions that it leaves us with, my theorist colleagues have been hard at work for so many years trying to develop pulsar emission models. And we've made stellar advances, especially with advances in computational capabilities in terms of tying together the pulsar magnetosphere with the observed radiation. The other thing is this picture is very well understood if you're trying to look at the radio emission, especially from younger pulsars. But when you're looking at high energy emission or optical emission from older recycled systems, it's not very clear to us, or the models are currently under construction. So the question is, how does the detection of UV millisecond pulsation change our understanding of pulsar emission models? Is it going to fit in with the conceptual understanding that we have right now, or it's going to allow us to expand further? And the last hope that I would leave you with is this discovery tells us, and the discovery of SAX-80 that was done in the last 1.5 years, that future missions can help us identify more of these untapped sources. And they're out there. Thank you.
All right, with that, we're going to begin our lost the mouse, final Q&A session of the meeting. So if you're watching on Zoom, be sure to use that Q&A feature to queue up your questions. And if you're here in the room, please raise your hand high so Zilly can see you. And for both groups, please be sure to state your name, affiliation, and who your question is for.
Hi, yeah, my name is Ryan. I'm from the University of Kentucky. And I actually have 2 questions. Should I just ask one or?
Let's start with one and see
Sure.
see what we get to.
So I have a question for Eric. When you were showing those, the light curve, I don't know if I'm making this up, but so you're looking at the W1 filter on Swift and then the X-ray light curve too. It looked like those were, it looked like the peak of the UV light curve kind of occurred at when the X-ray dipped. Am I making that up? Did you look at that at all, or?
So yeah, so there was definitely, I didn't really talk about it, but the subject of 2 actually prior papers to the one that I was talking about looked extensively at the behavior of both the X-ray and the UV emission for this source. And so it showed, the thing that I'm thinking of is that it kind of showed that transition where the X-ray was originally below the UV, and then it switched over to become X-ray dominant over the UV emission. So at the time we were thinking, they were thinking that had to do with the state transition of the accretion flow around the black hole, and in some way analogous to like a microquasar system. So that was the thinking, but yeah.
One more question.
Yeah, go ahead.
Yeah, so this is for Amruta. So yeah, that was really interesting. I was curious, did you at any point kind of look at like a ratio between soft X-rays and hard X-rays and seeing how that varies with time in these kind of transitional systems?
Yeah. I don't know if my mic is on.
Can you bring it closer to yourself?
Oh. Hello, can you hear me now?
Yeah.
So since we have the NuStar and the XMM Newton data, we've been able to do joint fits and look at the ratios over time during transition. And we don't see a lot of change in the spectral index during different modes as well. So yeah, and we don't have a data set that is right at the time of the transition from 2013. So we have the data set which is after it has changed configuration, right? So we've been able to look at that data and look at how they change with the light curve variabilities, but not directly at the transition. So that's what I would like to do. And we have proposals standing in for when the next transition happens.
Great. I also want to really quickly welcome Rose's collaborator, Shuo Zhang, to the room via Zoom. Shuo, you're here with us if you want to turn your camera on. Sorry about that. Thank you. All right, Govert.
Govert Schilling, freelance from the Netherlands, with a question for Eric. At the virtual 237th meeting of the AAS 2 years ago, Anna Payne of the University of Hawaii presented, well, you know about it, the object assassin SN something, which was back then presented as the first example of a repeating partial TDE. So I was wondering what is so special or unexpected about your find. The other thing, when I was reporting on this discovery 2 years ago, I was in touch with French theoretical astronomer Jean-Pierre Luminet, who apparently predicted these kind of events already 36 years ago. And he told me that he was surprised that so few had been discovered because he expected almost all TDAs to be repeating partials. I was wondering if you could comment on that.
Okay, so Assassin 14 KO is periodic in the optical UV. And so the X-ray emission, I'm pretty sure, is much more stochastic. And so for FYK, we actually see the resurgence in both the X-ray and the optical UV simultaneously. And we think that that probably has to do with the proximity of the returning star to the horizon of the black hole. So for 2018 FYK, we think that the pericenter distance is highly relativistic. So probably not more than like a few Schwarzschild radii. And that's really what's leading to the periodic flares in the X-ray. There's also the difference in the time scale. So 14 KO is 114 days. And it's, you know, it repeats like 114 days plus or minus one. It's really fascinating. Whereas we only, of course, have one example so far for FYK, but we're waiting. In terms of whether or not all of these systems should repeat, it depends on what you think the mechanism is for binding the star to the supermassive black hole. So there was kind of it was sort of almost an aside in that animation that I showed where it was discussed that the star that's being repeatedly partially disrupted was originally part of a binary system. That's because if you have just a single star that comes in and is partially tidally disrupted, tidal dissipation alone is actually not capable of binding the star to the supermassive black hole with a sufficiently short period. So you need an additional dynamical mechanism. In this case, it's called Hill's capture to do that. So I don't know why Luminae was thinking that these things should all be doing this. But yeah.
Okay, got some questions here further back. We'll get to all of them. We've got time.
All right, thank you. This is Ethan Siegel from Starts with a Bang. Rosa, I'm glad your advisor is here. This question is for you, and I felt bad composing it knowing you're an undergrad. So I'm happy you have an assist if you need it. So I wanted to ask, with respect to the double flare, the very first Sagittarius A star flare that you showed in the X-ray appears to have a small, you know, when you subtract out the Gaussian feature, it has a small peak followed by a small dip with respect to the Gaussian. This isn't the only such flare to have such a shape. Do you have any idea what the physics behind this early part of that flare might be? And if that might provide a clue to the nature of the double peaked flare you showed later?
Thank you for the question. I'm not sure if there's any relation between the going down and up in the light curve with the double peak flare that we found in 2018. The first flare light curve that you were talking about, is it the Chandra light curve that I showed firstly? Yeah, the up and down might come from the residual, the error from the observation. And because of its Chandra observation, the light curve is continuous, while new star light curve is not. The 2018 double peak flare, there has to be a different mechanism. We don't know why the magnetic field or some physical condition can recover so fast, enabling that second higher peak. So that is exactly why theorist observers are fascinated by this double peak flare. This is actually the first double peak flare that new star detected with full profile. Earlier in Chandra observations, they have detected actually multiple double peak flares, but this one is the only full double peak flare that new star detected. So we are excited to see that.
Great. Okay. Got one from Martin up here.
Hi, Martin Ratcliffe Evans in Sutherland and Freelance. Hopefully I can have a two-part question, one for Eric. You were invoking in your model you said that stars were in a few thousand-year orbit and that somehow they get into a very short period orbit. In the center of our Milky Way, most of the stars around there are, less than 100-year orbit. So it seems to be normal to have stars very close to the supermassive black hole. So I was curious why you need to invoke this very long period being in a binary and then being tidally captured. And then the second part is, Emily, I think what you're describing with the absorption and the peak is what I'm familiar with as a P Cygni profile. And if it's a P Cygni profile, usually you have a hot photosphere behind you and you have a black hole. Is it the accretion disk causing the illumination for that absorption dip next to the peak? And I may be totally wrong there, but that's my question.
So the stars in the galactic center you're referring to are the S stars, and those are actually thought to be maybe produced by the same mechanism that I was describing. The only subtlety there is producing the eccentricities of the S stars, because they're actually smaller than you would predict from Hill's capture, this dynamical exchange. So the difference is really primarily in the point of closest approach of the original binary. So what has to happen is that the binary has to come close enough such that its point of closest approach is at least comparable to the tidal disruption radius of one of the individual components within the binary, which is statistically less likely.
An answer to your question to me, I'm not entirely sure. I mean, I'm not entirely sure how to answer the question. I'm sorry. The material that would be traveling at us would most likely be blocking almost all the material that might be like in the background or traveling in a different direction, because it's a very puffy torus and accretion disk. I don't know. Sorry. Okay.
Do we have any questions online right now? Nope. Okay. Any other questions in the room? I see Ethan's got a hand up back there.
Hi, this is Ethan from Starts with a Bang again. This question is for Eric. Eric, I wanted to know, we know that certain mass stripping events, as well as very close passages to a black hole Schwarzschild radius, can perturb an otherwise reliable orbit. And I was curious about how robust your prediction for abrupt dimming in August 2023 is against such possible perturbations.
Yeah, that's an excellent question. So the point of closest approach of the star is highly relativistic, we think, but the orbit is also highly eccentric, like eccentricity is 0.99 and up, which means that the vast majority of the time in its orbit is spent at many, many more Schwarzschild radii. So there is an effect. So there's general relativistic advance of periapsis, but that really just rotates the orbit and doesn't affect the timescale too much. There is a gravitational time dilation effect, but again, it's near pericenter, and so it's really only for that time that it passes through there. So it's definitely an effect, but it's probably not on a time scale. It probably won't change things on more than like a single day time scale tops, I would say. So I think it's fairly robust. We'll see though.
So you don't worry about like the possibility of having mass being stripped off of the passing star unevenly in a way that changes its momentum enough to maybe alter its orbit? Because you've only seen one orbit. You don't have like, oh, I know it's stable.
Sure. Yeah. So okay, it's kind of a technical answer, but the angular momentum of the orbit itself is actually much larger than any angular momentum you could give to the star without completely destroying it, which is a possibility. But because of that, it's really hard to change the physical pericenter distance of the star substantially. There's also a possibility, which is that you can actually, through asymmetries in the tidal interaction, actually kick the star out. But because of the Hill's mechanism and the capture process, the star is actually much more energetically bound, and it's therefore difficult to overcome that energy barrier and achieve kicking the star out. Does that kind of make sense?
So are you saying that that the perihelion of the star, or whatever we say for a non, star, and the semi-major axis of the star's orbit are unlikely to change because of these effects?
Yeah, the term I've seen is peribothron.
All right, new
So-
word for all of us today. Cool. Further questions in the room? Yep, I see one back here.
In the back.
Oh, sorry, yeah, sorry. Missing the third dimension there.
Hi, Hannah Redhead, Sacramento State. My question is for Eric. I was wondering if you were aware of any like theoretical predictions for how many repetitions you expect for these partial TDEs?
Yeah, great question. So it depends extremely sensitively on how close the star actually is to the supermassive black hole. So the distinction between like effectively nothing happening, being partially disrupted, and being completely destroyed changes as a really like, you change that pericenter by not very much and you go very quickly from one to the other. So it really depends precisely on where the star is in its orbit and its point of closest approach. And I have toyed around with trying to simulate some of this stuff hydrodynamically. And I think, unfortunately, it's just a matter of initial conditions effectively as to where the star began. So what we've been able to potentially gather from the observations is that somewhere between 1 and 10% of the mass of the star is being liberated each time it goes through pericenter. And the uncertainty there really comes from the fact that we don't actually have enough data at the wave bands that we think a good fraction of the energy could come out at. So if it's 10%, then it's more likely that this thing is only going to survive for maybe 2 or 3 more encounters with the supermassive black hole. If it's 1%, maybe we've got like a couple decades worth of pericenter passages. But yeah.
Cool. Okay, well, I have a question for Amruta. I'm curious about this whole concept of pulsar recycling. So the very existence of the pulsar graveyard implies that the recycling process is pretty fast, because otherwise there would be pulsars populating the graveyard as they're making that transition. So what is the timescale for a pulsar to become a millisecond pulsar?
Okay, that's a great question, actually, and I've never thought of it that way. But if you look at the timescales of pulsars that are in the younger section, or like the younger class of pulsars, we see pulsars that are up to a few thousands of years old. And then in the pulsar recycling mechanism, or the process itself, can take millions of years. And the older recycled population, when we talk about it, it's up to few million to few, 10 to the power of 9, which is about few thousand million years. So, which is why I think we don't see as many pulsars that have come back up in the millisecond pulsar population. The other thing is, it is also possible that we need more sensitive instrument to be able to find a population that's fainter. So, yeah.
Awesome, thank you for that answer. Do we have any further questions either in the room or online? Oh, got one.
Okay, hi, I'm Ellie from Holy Valley High School, and this question is for Amruta. It's kind of simple, but have there been any other ultraviolet millisecond pulsars discovered?
Yeah, so as I understand your question, have there been any other UV millisecond pulsars discovered? So yes, in the last year, there was another system that was discovered. Also, they used the same setup that we had for discovery of this system, which is using Hubble Space Telescope with specific configuration of STIS. And they found UV millisecond pulsations in a system called SAX 1808 at a level of about 2.5 milliseconds, which is the spin period of the pulsar in that system. But we haven't discovered anything purely blindly where Hubble would discover it without us a priori knowing the period of the system.
All right, so with that, let's draw our final press conference of this meeting to a close. I want to thank you all so much for being a wonderful audience all week, and a big thank you to all the PIOs who've helped us prepare press releases, to our excellent audiovisual crew, as well as to our sponsor, the University Space Research Association. I will announce the date of our next press conference in a way, if you'll bear with me for 10 seconds while I screen share one last time. Hold, please. I would like to welcome you all to join us for AAS 242 in Albuquerque, New Mexico from 4 to 8 June 2023. So let's thank all of our speakers one last time.